In this lecture, I'm going to introduce ideas of protein energetics and dynamics. Aims and objectives for the session then are, first of all, to understand the need to look at protein energetics, why this is interesting, and to survey the molecular forces and how they can be used to study protein dynamics. At the end of the session, you should be able to describe the different types of forces and describe a simple force field and how it can be used in the computational analysis of proteins. The first point really is that proteins are mobile. So that ranges from the sorts of large-scale movements seen here in assembly of a bacterial pilus through to much smaller, detailed movements. So taking hemoglobin as an example, there are 4 subunits shown coloured in blue, cyan, yellow and green, with the heme groups and the bound oxygens shown in pink and red. If we rotate this to get the best kind of view of how you can access the oxygen molecules, particularly here in the yellow and cyan chains, you can see that there appears to be a path to the surface. However, if we space fill that, you can see that there's no access. So that means that in order to get oxygen in and out, there must be flexibility of the hemoglobin molecule to allow that to happen. So this is a simple animation showing the oxy and deoxy states, and you can see indeed that between these two states there is quite significant movement of the protein. Here's another example where we're looking at a molecular dynamics simulation of a small protein. And you can see it moving around. You can see there's a ligand which is shown in the sort of large white spheres that's in there as well. And this again gives you an impression of the amount of movement that proteins undergo. We will come back to molecular dynamics later. For now, we're going to start looking at forces within a molecule. So we can divide the types of forces into 2. We have covalent interactions and non-covalent interactions. So the covalent interactions are based on bonds between atoms. So if we think of a protein sequence, the primary structure of a protein, with the exception of disulfide bonds, all of the covalent interactions are local at the sequence level. So they're either occurring within amino acids or through the peptide bond between adjacent amino acids. We do, of course, then also have disulfide bonds that can link cysteines from remote parts of the sequence together. Non-covalent interactions, on the other hand, at the sequence level can be local, so there can be adjacent side chains interacting with one another, that sort of thing, or indeed side chain atoms interacting with one another within an amino acid. But also we get long-range sequence level interactions. So as the protein folds up, perhaps the N-terminus and the C-terminus come together in 3 dimensions. Let's look at the covalent forces first of all. So the most obvious one is the simple covalent bond, which is basically, of course, the sharing of electrons between atoms. And what we can look at in terms of just 2 atoms bonded to one another is the length of that bond. We can define the van der Waals radius, which you can think of as being like the spherical radius of an atom. We'll come to the proper definition a bit later. We can also define a covalent radius, which is for two atoms it is the half the sum of the distance between the centres when those two atoms are the same. So, as I mentioned with that last slide, the fundamental thing that we have there is a bond length, the distance between those two atoms. Now, we've already defined that in terms of the covalent radius, but of course we can stretch and compress that as well. In addition, the other two types of covalent forces are bond angles and torsion angles. So the bond length is basically simulated by thinking of a normal spring. So Hooke's law describes the action of a force on a spring either stretching or compressing it. And his law is summarised by the very simple equation of F equals KBS, where KB is some constant that defines the amount of force needed in order to stretch or compress the spring. S is that amount of stretch, which, just to be confusing, I've called X in this diagram. So because the force is directly proportional to the amount of stretch, that means that if we put a single weight of, let's say, 1 kilogram onto this spring, then we stretch by an amount X, and if we put double that weight, so 2 kilograms, then we'll stretch by double that amount X. So every bond has an optimum length, which is the sum of the bonding radii. That's a bit like thinking about a spring that is sitting there without a weight pulling on it. So what we do is assume that bonds just obey Hooke's law, which just says that the extension, the stretch, is proportional to the force. So force equals K, some constant, times the stretch. So when the bond length is optimal, then there's no force, because there's no stretch. If, however, we've got a non-optimal bond length, so this is the observed bond length minus the optimal bond length, and that of course is the stretch, then the energy to stretch the bond from its optimal position to this new position, or indeed compress, is obtained by integrating this equation, and we get the energy is half the constant times the stretch squared. Now, of course, the next feature of a bond is that often atoms such as carbon don't just bond to one other atom, they can bond to two or more. And depending on the hybridization of the atom, we get different optimum bond angles. So the bond angle, of course, is defined by the, in this case, hydrogen, a carbon at the middle, and another hydrogen here. So given that this is the case, in the case of a sp3 hybridized carbon with equivalent atoms at all four vertices, then the optimum angle is around 109.5 degrees. In the case of sp2 hybridization, where we've got a double bond, then the optimum angle here is around about 120 degrees. So, given that every angle has an optimal value, such as the tetrahedral carbon being 109.5 as we just saw, then we can think of that angle as a spring in just the same way that we did for the bond length. So here I have an sp3 3 hybridized carbon with 4 groups attached to it, and on the right I've just shown it rotated. So I've taken off these 2 dark grey atoms and just show you the projection of these 3 atoms here, the red one and these 2 white ones. So if we define this angle here as theta, then again we've got an optimal angle theta naught and an observed angle theta. So the energy again is obtained by integrating Hooke's law, and we get the energy equal to half some constant multiplied by the deviation from the optimum squared. Now the third type of force is the torsion angle or dihedral angle. So what you can see in the animation on the left is 4 atoms shown in red, green, blue and purple, and I'm rotating them about an axis between the 2 atoms in the middle. So at this point here you get the projection that you see on the right. So the green atom is exactly behind the blue atom. And on that basis we can calculate an angle between the red, the blue and the purple atoms. So that's what's known as a torsion angle. Now in the case of torsion angles we can't use Hooke's law because of steric effects. So you've probably seen these so-called Fisher projections before, where the small circle represents an atom close to you, the big circle represents an atom farther away from you, and you can rotate this bond between the 2 atoms. So in this case we can have an eclipsed conformation like this, where the atoms that are attached to the 2 central atoms are kind of on top of each other in this view, or you can have a staggered conformation like this, where they're positioned apart from one another. Now these staggered conformations are energetically favourable compared with the eclipsed conformations because of the steric effects of these atoms interacting with one another. So what I've done on the right here is to select about 50 phenylalanines completely at random from the protein data bank. I've then fitted them on their backbones, so the N, the nitrogen, which will be down here, the C alpha here, and the C carbon. And then I have just drawn the positions of where those side chains end up. And you can see very nicely there that there are 3 kind of clusters of positions. There's one very heavily populated cluster here, which is quite tight. There's another cluster here which is a little bit more spread out, and then a third cluster here with only 2 members. In the case of the energy function for a torsion angle then, what we need is some sort of function that will mimic the minimum energy for the staggered conformations and the maximum energy for the eclipsed conformations. And what we can use for that is a cosine function. Now a cosine has the property of having a maximal value of 1 at 0 degrees and of course 360 degrees, and a minimal value of -1 at 180 degrees. Now of course that's not what we want. We do indeed want to have a maximal value at 0 degrees and 360 degrees, but we also need to have maximal values at the other eclipsed conformations of 120 and 240 degrees. So what we can do is simply multiply the angle by some constant in order to get the correct repeat. In this case we want to have 3 maxima and 3 minima instead of just the 1 that occurs at 0 and 360 degrees, which of course is the same value. So if we put a constant m here of 3, then we will get a curve that looks like this, with maxima at 0 or 360, 120, 240, and minima at 60, 180 and 300 degrees. Now what we've also done here is to add an offset of 1, which means that we get a range going from 0 to 2 instead of -1 to +1, and then we've put a half in front, which means that we go from 0 to 1. And then of course we also have some constant representing the amount of force that results from this staggered versus eclipsed conformation. Okay, we're going to take a break at this point, and I want you to do a couple of little exercises. So you're going to visit a Hooke's Law simulator on the web, and this is using springs rather than bonds, but it's exactly the same. So I want you to go to this URL, fet.colorado.edu/sims/html/masses/springs/latest/masses/springs_en.html. On that page, click Intro, and then over on the right towards the top there is a checkbox that says Movable Line. So click that, and then there will be a line that will appear underneath the two springs. Drag that to the bottom of the springs, and then add a weight of say 100 grams to one of the springs, and it will start bouncing when you've done that. So click the red stop button by the top of the spring to stop it from bouncing. Add a different weight, let's say 50 grams to the other spring, and again click the stop button. So there are a number of different weights available there. That pair of 100 grams and 50 grams is probably the most obvious pair to look at. So what can you say about the stretching of the spring compared with the chosen weight that you added? Then go on and experiment with some of the other simulations you can do. So there's another simulator of Hooke's Law as well, provided on the same site, and you can take a look at that one as well. In the second part of the lecture, we're going to look at non-covalent interactions. So these fall into three groups: electrostatics, van der Waals packing, and hydrogen bonds. Electrostatics are interactions between charged atoms. So like charges repel, unlike charges attract. Now these can be between atoms with a formal charge, so a +1 or a -1, but in fact, because of the distribution of electrons in organic molecules, even atoms without a formal charge will have partial charges which interact. The formula that we use to describe the energetics of electrostatics is simply Coulomb's law. So Coulomb's law states that the energy is the product of the two charges divided by 4 pi epsilon naught r squared. Epsilon naught is referred to as the permittivity of space, or the dielectric constant. You can see from this equation that if Qi and Qj, the two charges, have the same sign, then whether they're both negative or both positive, the resulting energy will be positive. Whereas if one of them is positive and one of them is negative, then the resulting energy will be negative. However, Coulomb's law assumes a vacuum. So this permittivity of space, this dielectric constant, is based on the idea of either a vacuum or a completely homogeneous space between atoms with different separations. Of course, that's not really the case in a protein, where you may have other atoms between the two atoms of interest. So R squared is often replaced with a term epsilon r times r, where epsilon r is known as a distance-dependent dielectric. That means depending on the value of r, the value of epsilon r varies, and therefore can take account of the likelihood of seeing other atoms between the two atoms of interest. Next we come on to the van der Waals forces. So these have both repulsive and attractive elements to them. The repulsive element is very short range and results from electron-electron interaction. You can think of it like two rubber balls, and once you start to push them into each other, they're going to repel. The attractive or dispersion element is what's referred to as an induced dipole-induced dipole interaction, and this is somewhat longer range. So what happens is, if you imagine these are two atoms at the top here, and the electrons are moving around randomly. At some instance in time, you can imagine that atom 1 happens to have its electrons all spending more time over on the left here than they are on the right. And that means that there is a spontaneous dipole where we have more electrons on this side, and therefore a partial negative charge on this side and a partial positive charge on this side. What happens as a result is that the partial positive charge on this side of the atom attracts the electrons from this adjacent atom, and we end up then with a partial negative charge on this side and a partial positive charge on this side of the second atom. The partial positive and the partial negative attract each other, and we end up with an attractive force between the two atoms. Now this graph shows a typical energy profile as a result of that. On the far left, here we're getting the atoms pushing into each other with a very steeply climbing repulsive energy, positive energy. And here towards the right, as the atoms are separated, we get the attraction falling off between the two atoms. And at this point, where we have a minimum on this graph, we have the sum of the van der Waals radii of the two atoms. So this is actually the definition of the van der Waals radius. It's if we take two atoms of the same type, then the minimum on this curve defines the sum of the two van der Waals radii. Now the equation that describes this is shown over here on the right. We have a positive energy which falls off with power of the radius, the separation, to the power of 12. So obviously if you multiply a number to the power of 12, it becomes very big very quickly, and that means that the repulsive effect is only very, very short range. The attractive effect on the right, so this has a negative sign in front of it, this falls off to the power of 6, so also falls off pretty quickly. Atoms have got to be fairly close to one another to have an attractive van der Waals effect, but this nonetheless is a much slower fall off than the repulsive effect. And these two constants here, Aij and Bij, depend on the nature of the atoms I and J. The third type of non-covalent interaction is the hydrogen bond. This is an interaction between a hydrogen bound to an electronegative atom, and in the case of proteins that means an oxygen or a nitrogen, and a lone pair of electrons on another electronegative atom. So this is mostly a charged type of interaction. It's a dipole-dipole interaction. At the bottom here, in the figure at the bottom, we can see a water molecule which has hydrogens attached to an electronegative oxygen. The hydrogens have a partial positive charge and the oxygen has a partial negative charge. Now the thing that is important about this is that unlike normal electrostatic interactions, these interactions are very directional. There's a clear angle that's important as well as just the charges. Up here on the top right we have an example of a hydrogen bond occurring between an asparagine and a tyrosine in a protein. Now this is a visualization from 2013. This was the first time this was seen, where you could actually see hydrogen bonds by atomic force microscopy. So here we've got a number of molecules, and this is a diagrammatic representation on the right, and you can see where the network of hydrogen bonds is. You can actually see them in this AFM image on the left. Now if we want to describe a hydrogen bond in some sort of equation, we can include an explicit equation for it. Essentially, as I said, it's electrostatic in nature, but the fall off, the rate of fall off of the interaction is much faster than with a normal electrostatic interaction, and it has a clearer kind of minimum distance to it as well. So we can use a Lennard-Jones style potential, the same sort of thing that we used for describing van der Waals interactions, and we can include an angular component in that as well. However, most people when they're simulating proteins and looking at the energetics of proteins don't actually bother with a separate term for this. They just include it as part of the normal Lennard-Jones van der Waals interaction potential. Doing that means there's no great loss in accuracy, but it does speed up the calculation significantly. And if you're interested, there is a paper cited at the bottom here which discusses including explicit terms for hydrogen bonds or not within potentials. Okay, so assuming we don't actually have a separate term for hydrogen bonds, we can bring all these things together. At the top here we have the energy for stretching or compressing bonds. Then we have the term for stretching or compressing angles. And then we have our term to deal with torsion angles. Then the Coulomb's law to deal with electrostatics. And finally our Lennard-Jones potential, which deals with the van der Waals interactions. At this stage we're going to take another break. And we've got two different simulators for you to have a look at. The first one here is a simulator of Coulomb's law. So when you go to this website, click macro scale and then experiment with moving the two spheres which represent two charged atoms. Experiment with changing their charges, and in particular try making them both positive or both negative, and you'll see that the forces will become repulsive instead of attractive. And secondly, a van der Waals interaction simulator where you can drag the atoms apart and then watch the simulation of them vibrating under the force. you can switch on the display of the forces, and you can try changing the atom types. You may need to scale the graph, particularly if you choose both oxygens, so that you can see the whole of the graph. For the third part of this lecture, we're going to look at how we can use this energetic potential that we've developed in order to understand how proteins work and how they can cause disease. So to understand these sorts of things, we need to understand the dynamics of proteins, how they move. The example that I gave you at the beginning of hemoglobin and how that needs to be flexible in order to allow oxygen to get into the oxygen binding site. In addition, we need to understand folding, which will be the topic of a separate lecture, and we need to understand the energetics of proteins in order to understand things like enzyme catalysis. And of course, we wish to be able to simulate these sorts of things in a computer. We've already looked at the way that we can simulate, or at least represent, the energetics of a protein in a computer by looking at the three types of covalent and three types of non-covalent force. Now, covalent bonds are in general, as I said at the beginning, local, so they're occurring within amino acids or between adjacent amino acids. The one exception to that is the disulfide bond. And don't forget, the disulfide bond is not a type of force. It's not any different from any other type of bond. It's just between different atoms. Non-covalent interactions, however, can be distant, and therefore the time taken to calculate all the possible interactions between all the atoms is going to be proportional to the number of atoms squared. Now, that can really result in slowing down a calculation when we've got a large protein. So in practice, what we tend to do is use some sort of cutoff, by which I mean that if the distance between atoms is greater than this cutoff, we don't bother to do the calculations, because as we saw for the van der Waals interactions, the Leonard-Jones potential, there's a very, very rapid fall off in the energy, and for electrostatics it goes with roughly the square of the distance. So what we could do is simply truncate the energy calculations. As soon as the distance becomes larger than some cutoff, then we ignore this particular interaction and don't include it in our calculations. This is shown in the graph on the right by the red line. The black line represents the actual energy with no cutoffs. The red line then follows the same trace along here until we get to this point where we've applied a cutoff, in this case of 14 angstroms, and above this we get a sudden jump in the energy. Now that means that we get large fluctuations in the energy and we can have problems in our simulations. The next possibility is what's known as shift, and what's done there is that the whole potential energy surface is modified such that the energy reaches zero at the cutoff of interest. So that's shown in the graph by the green trace following here, and we hit this zero energy at this cutoff of 13-14 angstroms. But what you can also see from that is that the minimum here is somewhat different, and that means that the equilibrium distances are all slightly decreased, and that will have some effect in errors in the simulation as well. And the third option, which tends to be the preferred approach, is what's known as a switch, and that tapers off the effects of electrostatics or whatever it is we're looking at over a range of distances. So in this case we're starting to fade out the energy potential that we're looking at around 10 angstroms, and by the time we get to 14 it is back to 0. So that means that we're getting a gradual transition between this curve, the correct curve, the black curve, and this one where we're not bothering to do any calculations anymore. So that kind of has the best of both worlds. Obviously there is a transition which is unrealistic, but we don't get these sudden jumps in energy, and we don't displace this minimum in the curve. So once we have an efficient way of calculating all these values, we can do simulations known as molecular dynamics. And these simulations rely on Newton's second law of motion, which simply states that the acceleration of a body is directly proportional to and in the same direction as the net force acting on the body, and inversely proportional to its mass. So this is hopefully a fairly familiar equation of F equals ma. So force equals mass times acceleration. And rearranging that, of course, we get acceleration equals force divided by mass. So what we can do with molecular dynamics is give the atoms all some initial position, which would come typically from a crystal structure, and choose some short time step, usually on the femtosecond time scale. We can then, using the sorts of equations that we've talked about, we can calculate all the forces on all of the atoms. We know the masses of the atoms, and therefore we can calculate an acceleration. We can now update the position of all the atoms by applying the acceleration and the velocity, and then we can take a time step and repeat the whole process. Recalculate the forces, move the atoms, take a time step, and so on. What we generally do to initialize that is assign each atom a random velocity, and to do that we can use a Boltzmann distribution which relates kinetics to temperature. So we choose a temperature, we can assign random velocities to each of the atoms based on that distribution. We can then calculate the force on the atoms, we calculate the acceleration, we take a time step, finding new positions and new velocities. In practice, what we tend to do is use some variant of what's known as the Verlet or leapfrog algorithm, and this simply separates the calculation of the velocities from the updating of the positions. So we're kind of, as you can see in the graph, we're doing a leapfrog of one compared with the other, and this just improves the smoothness of what we're doing, which is effectively just integrating Newton's laws of motion. So here's a very simple molecular dynamics simulation. This is deposition of an atom of copper onto a copper surface. So this comes from kind of physics, chemistry area rather than looking at proteins. But you can see as that atom landed on the top of this surface, it transfers all of these vibrations. You could see a little attraction to start with, the atoms on the surface coming up towards the approaching atom, and then there's this kind of ripple effect throughout the structure as the atom lands. This is a graph or a simulation that I showed you right near the beginning, where we're seeing the molecular dynamics of a small protein and a ligand bound to it. Now, what are all those little red and white things around the outside? Well, they're water molecules. And you can see the number of waters is actually quite significant compared with the number of protein atoms that are in there. And indeed, the number of waters can be absolutely huge when compared with the number of kind of interesting atoms. So what I'm showing on the right there is a protein embedded in a box, and all that little kind of red and white sort of bits scattered around here are water molecules. So we actually end up having to waste a huge amount of time calculating the energy of water. Now, we can miss out the water. We can do a simulation in vacuo, but this really reduces the accuracy hugely. Now, there's another problem with water, which is that if it's allowed to move around in a box, as we showed there, you're going to have effects of the water actually wanting to move outside the box. If you constrain it to the boundaries of that box, then again that's going to cause problems with the simulation. So what we do is actually embed this box in a three-dimensional lattice of other boxes, and if, for example, this atom were to move to the right and enter this box, then what we do is pretend that it came in on this side of this box. So as this atom moves over here and approaches this atom, because this is a copy of this one, then we make it come in on this side. So in reality we only actually simulate the middle box, but we allow atoms to move as if they were entering another box by pushing them in on the other side. Okay, at this stage we're going to take another short break, and I want you to look at the Wikipedia page about molecular dynamics. Don't worry about the detail unless it's something that particularly interests you, but do read the following three sections: history, area of application and limits, and some examples of applications. So what can we do with all this? Well, we can look at protein dynamics, how proteins move. We can study how they flex internally. So the example that I gave earlier of the entry of oxygen into hemoglobin is a good example of that. We can also look at the energetics of protein movements, how easy or difficult it is for a protein to move. We can also use dynamics to look at refining modelled structures that we produce from so-called comparative or homology modelling. This is where we take the structure of one protein and use it to build a model of a homologous protein. Now that of course may involve replacing loops because they're of different lengths, and of course there are lots of side chains that will need replacing. So in that process the joins where we've spliced in a new loop, or the side chains that we've put in may clash and the geometry may be wrong. So we can use protein dynamics and energy minimization in order to resolve those problems. So in the case of energy minimization, what we're trying to do is find a global energy minimum. You can think of that a bit like cooling a protein down to absolute zero, the conformation it would then adopt. Now, the problem with energy minimization is that you can visualize the energy as a surface in multiple dimensions. And the problem with that surface is that it's very rough, and therefore there are lots of local energy minima. So if we just do an energy minimization, what tends to happen is that we get trapped in a local energy minimum. So we can use molecular dynamics as a way of being able to get over those local energy barriers by putting some energy in other words, having a slightly higher temperature. So what we can do then is run a molecular dynamics simulation, take snapshots at different time intervals, and then we can energy minimize each of those to try to find the one which has the lowest energy and is more likely to be a real energy, global energy minimum. The other thing that we can do is use these potentials that we've developed, or at least the non-covalent part of the potentials, to calculate the energy of an interaction between, for example, two proteins, or a protein and a small molecule. Now, that doesn't take into account the hydrophobic effect and the effects of entropy, but there are ways that that can be done using molecular dynamics and what's known as an energy cycle, but that's too much for us to go into now. For the moment, we'll just talk about the idea that if we did molecular dynamics, we could in principle simulate how say a small molecule drug would interact with a protein and dock with it, but the problem there is the timescales. It's really quite difficult to do molecular dynamic simulations of a protein that last for more than generally a nanosecond or perhaps up to a millisecond, whereas in the timescales necessary for docking are probably more along the up to a second timescale. So what we can do instead is use sorts of search protocols to try and work out how proteins might interact with each other or with small molecules, but then we need to score each pose, as it's known, each orientation of the two molecules coming together, and we can use these sorts of potentials for doing that. We will return briefly to this a little bit later. On the other hand, what we cannot do with this is protein folding. We cannot use molecular dynamics or other simulations based on this type of potential for protein folding. So why is this? Well, it comes down to hydrophobicity and the hydrophobic effect. The hydrophobic effect is known as the observed tendency of non-polar substances to aggregate in aqueous solution and to exclude water molecules. So you can see two very simple macro level examples of that below. On the left we have a layer of oil sitting on top of water, and on the right we have a water droplet sitting on a waxy leaf. Now, hydrophobicity is mostly an entropic effect. It's a result of disruption of a very highly dynamic hydrogen bonding network occurring between molecules of liquid water. As I mentioned earlier, water is really the consummate hydrogen bonder. It can accept two hydrogen bonds and it can donate two hydrogen bonds. So what ends up happening if you put something hydrophobic in, which is essentially something that is apolar and which cannot form hydrogen bonds, it means that the network of hydrogen bonds that water can make becomes oriented tangentially to this non-hydrogen bonding surface, thus forming a kind of ordered cage around the nonpolar surface. And this results in the loss of both translational and rotational entropy of the water molecules. We can take the different amino acids and divide them up on the basis of hydrophobicity. So hydrophobic amino acids are generally classified as isoleucine, phenylalanine, valine, leucine, tryptophan, methionine and alanine. Hydrophilic ones are the ones that really have good side chain hydrogen bonding. So threonine, serine, histidine, glutamate, asparagine, glutamine, aspartate, lysine and arginine. And somewhere in the middle are things like glycine, cysteine, tyrosine and proline. Obviously tyrosine has an OH group, but it also has quite a large phenyl ring which cannot form really good hydrogen bonds. Glycine is intermediate because it's so small it doesn't have a side chain, so it's not really either hydrophobic or hydrophilic. Cysteine of course has an SH group, and it's generally considered that sulfurs cannot form hydrogen bonds. However, we do sometimes see cysteines oriented in proteins in the same sort of orientation as if they were making hydrogen bonds. So it looks like maybe they can make very, very weak hydrogen bonds. And proline also ends up as being intermediate because it doesn't have a long extending side chain. Remember, the side chain wraps round onto the backbone. This idea of hydrophobicity of amino acids can be quantified. So there are a number of different hydrophobicity scales that have been derived. These have been derived in different ways. So, for example, there are partitioning methods whereby we mix water as a hydrophilic solvent and octanol as a hydrophobic solvent and add the amino acid to that. Then we shake it up in a tube, the two separate, and we collect the two parts and measure how much of the amino acid is in each of them. We can also take observational approaches. So we can take a set of protein structures and just look at those to see whether the amino acids are on the surface or they're buried. And based on the frequency with which that occurs, we can derive a hydrophobicity scale. There are also chromatographic methods that use reverse phase liquid chromatography, using a non-polar stationary phase and a polar mobile phase. There are physical property methods where we can measure partial molar heat capacity, transition temperature and surface tension. So there's a very nice review from 1987 in the Journal of Molecular Biology by Cornett et al., where they look at about 20 of these different scales and compare them. So the reason that we can't use something like molecular dynamics to look at protein folding is because of this concept of a hydrophobic core. This is not driven by the sorts of energy that we can describe in a potential. This is driven by this hydrophobic effect. So what I've done here is to take a typical protein and I've coloured all the hydrophilic amino acids in red, all the hydrophobic amino acids in blue, and then I've taken a slice through the middle, like cutting an apple in half. And you can see that not exclusively, but the bulk of the hydrophobic residues, the dark blue residues, are in the middle, and the hydrophilic residues, the red residues, are on the surface. Of course, there are a few of the blue hydrophobic residues that poke out onto the surface, and there are one or two of the hydrophilic residues that are buried inside. But as a general rule, we have this really obvious hydrophobic core. When I was talking about docking earlier, I said I would come back to that very briefly, and I'm not going to go into any detail about docking methods. If you do the BIOC0008 module in the third year, that's the bioinformatics module, then we talk some more about docking in that. What I am going to talk about a little bit more is just to focus again on the forces between molecules. The intermolecular forces then are all the non-covalent forces from the intramolecular set that we looked at earlier. So electrostatics, hydrogen bonds, the van der Waals energy, modelled by the Lennard-Jones potential, and the hydrophobic effect that we've just been talking about. Given these four types of intermolecular force, electrostatics, hydrogen bonds, van der Waals, and the hydrophobic effect, what do you think is the relative importance of these different forces? I'm going to take a very brief break at this point, during which I want you to have a think about that relative importance. Electrostatics, hydrogen bonds, van der Waals forces, and hydrophobic effect. Because remember that if you're thinking about two molecules interacting with one another, you have to compare their interaction with one another with their interaction with water. So have a think about that. Okay, so what you should have thought about was the interactions of each of these with water compared with interactions with one another. So let's take electrostatics first. Think about common salt, table salt. We know that that dissolves very well in water, yet it's an almost perfect lattice of charge interactions between the positively charged sodium and the negatively charged chloride. So if electrostatics were really that important compared with the interactions with water, then salt wouldn't dissolve. What about hydrogen bonds? Well, I've said a number of times that water is the consummate hydrogen bonder. So any hydrogen bonds that are occurring between residues within a protein equally well could be forming with water. What about van der Waals? Well, water's pretty small. It can pack against other amino acids and other molecules very well. So those van der Waals interactions could happen with water just as well as they could with another protein or with a small molecule drug interacting with the protein. So what's left? The hydrophobic effect. So just as in protein folding, which is driven by the hydrophobic effect, the intermolecular forces are really again driven by hydrophobicity. Now that doesn't mean that the other things aren't important, because if you imagine two completely hydrophobic surfaces interacting, well, that would probably give you the very best energy. However, you would have very low specificity as a result. So if all protein-protein interactions were mediated solely by hydrophobicity, then everything would be sticking to everything. So if you can make sure within that sort of hydrophobic interaction that all the electrostatics line up, all the hydrogen bonds line up, and all the van der Waals packing is as good as it can be, then you won't detract from the energy, but you won't add to it either. As soon as you get a mismatch of electrostatics, hydrogen bonds or van der Waals packing, then the energy of the interaction will not be so good. So by combining the hydrophobic interactions, electrostatics, hydrogen bonds and van der Waals, we can get both good specificity and good affinity. So this just looks at an example. This is an antibody shown at the bottom. This is the heavy chain and a light chain shown in blue and the sort of grey-green. That is forming a combining site at the top, which interacts with an antigen, which is in the paler green, the yellowy green towards the top. Now all those little red spheres are water molecules, and you can essentially see that the interaction between those surfaces of the antigen at the top and the antibody at the bottom are all pretty good, and where there are faults in those interactions, like down here and here, water molecules come in to fill those little gaps, and over here as well. So we have a closely packed interface, and you can see that also between the two chains of the antibody. We have good surface complementarity, and we have holes filled in with water molecules. Now, I mentioned that we get this idea that we have the energy being driven by hydrophobics, but we also want to match up those other things. So what I've done here is to take two interacting surfaces from a protein, and on the left I have this one protein here with the interacting region shown in this paler colour. I've then coloured the positively charged residues in blue, the negatively charged residues in red. And then I have lifted off the interacting partner and just shown the back view of the surface that's interacting with the structure on the left. So that means that I should have residues coloured on the right in the opposite colours of the things that they interact with on the left. And you can see I've drawn purple lines kind of joining up the bits that interact with one another reasonably well. There are a few residues that sort of appear not to be making quite the interactions you might expect, but some of those, don't forget this is actually a three-dimensional thing that you're looking at here. The things that are further away from you in this image are actually kind of closer to you when laid onto the top of here. So things like this blue patch down here are actually considerable distance away from this blue patch here. I also said we would mention briefly computational docking again. We can perform simulations of that. As I said, we can't do it with molecular dynamics, but there are search protocols for doing this, which we'll come back to in much more detail if you do the bioinformatics module next year. There are a number of problems in doing this. First of all, the search space. If we imagine we're doing a rigid body fitting of two structures, then we have a six-dimensional search space. If you hold one of the structures still, you can move, translate along X, Y and Z for the other structure, and you can rotate about X, Y and Z for the second structure. So that's 6 different dimensions that we can search in. The second problem is that that's a huge oversimplification, because of course they aren't rigid bodies. Proteins, as we have seen, are flexible, and in particular even a relatively rigid protein has quite a lot of side chain flexibility. And thirdly, of course, our old friend hydrophobicity, which is difficult to simulate in a normal sort of potential. However, these approaches really are pretty effective for small molecules, so interactions between small molecules and proteins. We can dock a small molecule into a protein quite effectively, and there are a number of different programs around for doing that. For protein-protein interactions, however, it seems to be much harder to get it right. For the last couple of minutes, I just want to point out a few errors that have been made in recent exam answers. So these are things that you should not make as mistakes, because I'm showing them to you now. First of all, this is a quote from somebody's answer a few years ago. Potentials cannot include hydrogen bonds explicitly because there are too many of them. That's simply not true. We can treat them explicitly, but there's generally no benefit in doing so. We just include them as part of the van der Waals and perhaps electrostatic potentials. That speeds up the calculations, and really the reduction in accuracy is very, very small. So suggesting that there are too many of them, well, there are far fewer of them than there are other things to consider, such as the van der Waals interactions and the electrostatics. Covalent forces include disulfides. I pointed this out as an error early on. A disulfide is just a covalent bond, just as the backbone bonds are and the side chain bonds. It's the forces that we're talking about. The forces come from the distortion of optimum bond lengths, optimum bond angles, and moving away from staggered torsion angles to eclipsed torsion angles. Third, we can use these potentials and molecular dynamics for protein folding. Well, that's what I've just been explaining. No, we can't, because the hydrophobic effect is really what dominates protein folding. We can use molecular dynamics to study the dynamics of folded proteins, and we can use the same potentials for things like energy minimization and for docking. So in practice, what we do for simulating protein folding is we use a different type of potential known as an empirical potential, which can sort of take account of things like hydrophobicity. And again, those will be described in much more detail in the bioinformatics module in the third year. So in summary, we looked at the importance of protein dynamics. We reviewed the 6 types of covalent and non-covalent molecular forces. So there are 6 of them altogether. 3 are covalent, 3 are non-covalent. We looked at their application in computer software, such as for molecular dynamics, and we looked at the hydrophobic effect and how important that is. We also examined briefly the 3 types of forces involved in intermolecular interactions, so the 3 non-covalent ones that are involved in intramolecular interactions, plus the 4th factor, which is the hydrophobic effect. So background reading, I recommend Lesk, Introduction to Protein Science, 3rd edition, pages 140 to 142.